Okay, so the second speaker of the morning is David Gamarnik from MIT. The title of the talk is Power and Limits of Local Algorithms for Graphs.
Well, thank you, and thanks for the opportunity to give 3 lectures. These lectures will be mostly with algorithmic flavor. We'll talk about algorithms, local algorithms. Let me tell you a little bit of what we're going to cover in each of the lectures. When I say local algorithms, I want to put a slash and say algorithm/methods. All 3 lectures will be about graphs, fairly simple graphs, simple undirected graphs. And in the first lecture, we will speak about partition functions, which really correspond to counting on graphs, the problem of counting on graphs. We'll talk about partition function limits in some structured type graphs. Specifically, we'll talk about irregular graphs with large girth. And I'll define everything, of course. In the second part, we will talk about, the second part will be genuinely algorithmic. We'll talk about, we'll consider the problem of counting, or the same as computing partition function. But we'll do that now for general graphs. So the first part will be structural. We will be looking at some limits, some structural graphs. We'll be looking at some limits and so on and so forth. The second part we'll talk about algorithms. And in both lectures, we will focus on local algorithms and methods. Methods that try to design algorithms by looking at just the local structure of the graph and ignoring its global properties. And that type of thing, that type of approach actually it works in many cases. And the goal of these 2 lectures is to demonstrate this power. Now, you already heard a couple of lectures on graph limits. Local algorithms do come up in the context of sparse graph limits, but I'm not sure that topic was covered. I think you probably heard about dense graph limits. But they do come up in the context of sparse graph limits, but that connection I will not talk about. I'll let others elaborate on that. So that's first 2 lectures. And the last lecture, we will talk about limitations, limits of local algorithms. Specifically, the limits of types of local algorithms which are called IID factors, which is a particular framework of local algorithms, and we will do that in the context of random graphs. Okay, so that's what we will do in 3 lectures. Let's get started. Let me just introduce some basics. As I said, we will talk about graphs, and the graph is a pair of set of nodes V and set of edges E. The graphs, all the graphs I will consider in these lectures are undirected. So what type of questions, what type of counting questions we're interested in this graph? So let me introduce 2 models, and we will focus entirely on these 2 models, although the variety of models and questions is broader than that, but we will just pick these 2 and drill deep there. So first model is the independent set model. An independent set in the graph, here's a graph. Independent set in the graph is just a collection of nodes, any collection of nodes such that there is no edge in between. So it's a subset of the set of nodes such that there is no edges in between. So if this is my graph, then I can take this node and this node and this node. If I didn't make any silly mistake, there is no edges in between. But I cannot add this node. That's an independent set. One thing I didn't say here is that the methods that we will use here, in fact, draw strongly on the methods from statistical physics. So statistical physics ideas have a very important relations to this discussion. And incidentally, statistical physicists call this object a hardcore model. So independent set and hardcore is the same thing. So what is the question that might be interested here? Accounting. We're interested in counting independent sets. So let Z be just a number of independent sets in a graph. Now, if the graph V has nodes, let's say V1, V2, Vn, that's a vertex set of the graph, typically this object is large. For example, exponentially large. So counting this such a thing algorithmically at least cannot be done in some trivial brute force way. It will take exponential time, and in the field of algorithms, we're interested in algorithms which are fast, namely polynomial time. Therefore, it's a non-trivial problem. And in fact, it turns out that this is a bad problem, in the sense that counting independent sets is what is called a sharply hard problem. A sharply hard problem. And I don't assume that you're familiar with algorithmic complexity theory, but just take it for granted that unless the world is completely different from what we know, unless things such as P is equal to NP, a major conjecture in the complexity theory, and $1 million prize Clay something, then similarly there is conjecture is that these 2 classes are not the same. A counting independent set is of that class. But we want to do that, since we cannot do that exactly, we want to do it perhaps approximately. So the question now is that, and that's the question we'll consider in this and next lecture, is can we at least approximately tell how many independent sets are in a given graph? With perhaps some additional assumptions on the graph. Okay, so that's what we want to focus on. Now, let's generalize the model a bit. Now, I have to probably stay above a certain line of visibility. Is that a reasonable? Do you see this line from the back? If you don't, I have to, not really, so even higher. So maybe this is the absolute lower bound. Huh? Move it. Okay. Not this one. Pull this one. Oh. I see. Now you see two silly lines there. Okay. All right. So let's now let's generalize it, and we will generalize. There's many ways to generalize the counting problems here, but we will just do focus on one way to generalize it. We'll fix a parameter lambda, which we call activity, and instead of counting independent sets, we consider the following object. Let's take the sum of the lambda to the cardinality of independent set and sum over all independent sets. So take an independent set and take lambda to the number of nodes of such an independent set and sum it up. And that's a generalized counting object, but if lambda is equal to 1, that's just the number of independent sets, so we're back to the previous example. So with this in mind, let's introduce a new object. Let's introduce the probability measure, which is called the Gibbs probability measure. And it's a probability distribution on the set of independent sets. So the support, the omega of that distribution, is a set of all independent sets, and it's very simple to define. The probability for every independent set I, the probability mass associated with that set I is simply, well, we want this probability to be proportional to the lambda to the I. But proportional means that we have to make it a proper probability distribution. So to make it exact, we just say that probability is equal to lambda to the I, cardinality of the independent set. But then we have to normalize it. What do we normalize it by? Well, this. Right? And that way it makes a proper probability distribution. Sum of the probabilities of I, independent sets, all independent sets, is equal to 1. And that's a Gibbs distribution. It's a very important object in both in graph theory and in statistical physics. Why do we introduce it? It's because, surprisingly, even though a priori we're interested in the counting questions, probabilistic reasoning helps quite a bit. So let's warm up with a couple of basic but important observations. In order to emphasize the graph under the discussion, I will put a sub-index G for the partition function. And I have to do that because if I change the graph, if I have a different graph H, then I'll have an associated partition function for that graph. And let me use the following notation. So if I have a graph G, and I have a node V in it, I'll write, with your permission, G minus V is deleting V from G. So just take this node, you delete it from the graph, and all the associated edges are also deleted from this graph. Stop me if anything is not clear. Basic things we should settle clearly. Okay, so here's a fairly straightforward observation, but useful at the same time. Call it a little lemma. I will also write subscript G to the probability to emphasize that the Gibbs distribution is with respect to a particular graph G as well. So here's the lemma. In the graph, given graph G and a node V, get it a bit higher, the probability, and now look at the probability of the following event. Generate an independent set I from the Gibbs distribution. So we have a Gibbs distribution on the original graph G. We generate the independent set, and we look at the event that the node happens not to be as a part of this independent set. So you have this node, some neighbors, and then you have some rest of the graphs, and so on. And this is node V. On this entire graph, I generate a random independent set I, and I'm asking, what's the likelihood that V is not part of that? That's some probability. Well, the claim is that you can write it as a ratio of two terms. A partition function associated with your graph G, but the top part is also a partition function. It's simply partition function of graph G, but with node V deleted. I leave it as an exercise. The proof of this fact is an exercise. It follows straight from the definition. What is the probability that what is the probability associated with this event? It's proportional to summing all lambda to the i's which do not include node V. Which means that you're essentially looking at all independent sets in the rest of the graph. Yeah? And then therefore something like this is true. Okay. So what? Well, then let's rewrite it slightly differently. Now, that means I can write the following identity. It's still original. Not in the independent set, times partition function of the reduced graph. Now I'm not going to make this as a lemma. It's just simply rewriting this algebraically. But then what I can do is I can continue this. I can do something similar for this reduced graph. And for conveniently, let me call this vertex V1, and there's no, this identity is true for any graph and any vertex. And so I could start with a vertex labeled 1 in my graph, and then I can continue. So this is equal to PG V1, not part of the independent set, times probability that in the reduced graph, let's say the second node is not part of the independent set, times the partition function where these two nodes are deleted. Thank you. And then I can continue. And when I continue, what I've done is I've represented, I can write the following identity. It's a product of V1 minus Vi. Graphs where the first I nodes are deleted, the likelihood that, or I minus 1 nodes are deleted, the likelihood that the ith node is not a part of the independent set. I going from 1 to n number of nodes. And inverse. Okay? Good. So the reason that this is a useful identity, although we hardly have done any serious work, it's a useful identity is because now I can, if I somehow can get a reasonable handle on these probabilities, for example, estimate them with some accuracy, then hopefully this gives me an estimate on the partition function as well. All right, but therefore, in some sense, but because problem is sharply hard, you realize that computing this probability must be sharply hard as well, and it is. But we will be able to compute this probability approximately, and furthermore, using local methods. So the genetic property, a very fundamental and important property that sometimes takes place, and we will take advantage of that, is that when you look at your entire graph and you have some node V, and you're interested in this probability, which becomes now a fundamental object, probability that node is not a part of the independent set, well, it turns out that with the right combination of the graph structure and parameter lambda, such probability is asymptotically equivalent to the probability that of the same event. Let me place this node somewhere in the center of the graph with respect to just a small neighborhood around this node, small appropriately defined. And if we have that, then there is a hope, okay, that because the neighborhood is small and have some structure, or perhaps it's just a small in terms of just the size, we will be able to compute that probability locally. So we will use the local methods to approximate this probability by looking at something like this. I should put some notation here, B, with respect to small subgraph B, and plug it into this formula and get the answer. Okay? So that's kind of the thinking that underlies this. And when you have such an identity, we said that we have the correlation decay property. Correlation decay property, meaning that the events associated with this node are asymptotically independent from things outside of the graph. Yes? This equation? Well, lambda, that's the reason that it disappears in this identity. It has to do with the property of independent set. If you look at other problems counting other objects, then it might not. But here it does. I mean, what is, you see, let's actually sort of give a quick, maybe verbal proof of that fact. What is this probability? You need to, it's a probability, it's a sum of masses of all independent sets which do not contain node V. Right? So the probability of that V is not in the independent set is sum of the elementary events where you sum over all independent sets such that V is not in that independent set. That's by definition. Right? But what is this? This is equal to the sum, partition function, lambda to the cardinality of that independent set. You sum over all the independent sets, right? But what is that object on top? So Z put outside. What is that object? That's a partition function of the reduced graph with this node V deleted. And that's so that's a proof. Yes? Oh, sorry, it was okay. The role of lambda. I thought the question was why the lambda disappears in this identity. That's how I heard the question. Okay, so that was a question. But that's another question is what's the role of lambda in this story? One thing is that when lambda becomes very large, this probability distribution starts concentrating more and more on larger independent sets. So, one impact of one sort of thing you can get out of here is that perhaps you can analyze largest independent set by pushing lambda to infinity. And interestingly, this kind of approach works for other problems such as matching, but not for independent sets because of some phase transition property associated with this presence or absence of correlation decay property. So in the next development, the value of lambda will be important. So now let me actually state a theorem that we will prove in the rest of the lecture, and maybe beginning of the next lecture as well. And has to do with now we'll reduce the space of graph to be deregular large girth. And let's define those first. So graph G is deregular if simply every node has degree D. And the degree of the graph is just the number of neighbors. So if every node has exactly D neighbors, we call it deregular. Okay? The girth G of the graph, girth, is the length of the smallest cycle. So you start with a node and you go around. If you can come back to it, that's a cycle. And the girth of the graph is the smallest cycle you can have. Now, consider the graph G, which is deregular and has girth at least some number T. And let's see how this graph looks locally. So this node has D neighbors. And each of these neighbors also have D-1 remaining neighbors. But they cannot be, if T is large, some number like 100, for example, you cannot have edges here because that would create a cycle. So they cannot be neighbors of themselves, so they have their own neighbors. And if T is large again, you cannot have neighbors between these neighbors of the neighbors because that would create again a short cycle. So they have their own neighbors. So the bottom line is that up until a certain depth, which is related to T, maybe T-1 or something that you can compute as an exercise, this graph locally looks like a tree, a regular tree. Yeah? So that's the idea. So if you have a deregular graph with girth bounded below by some number, then locally this graph looks like a tree. And in fact, it's a regular tree. Let me use the following notation. So T, D, a little t, is the graph, is a tree where all nodes have exactly the same degree t, so I have okay, and so on, and has some depth t. So all the nodes in this tree have degree t except for the leaves. Degree d. I said t. I'm amazed that you picked up. Yes, degree d except for the leaves, and t is the depth. All right, so theorem. We're given a sequence of graphs which are d-regular, and the girth diverging to infinity. Yes? That's easy. That's just finding a shorter cycle is very easy. Just I don't know off the top of my head, but that's an easy problem algorithmically. So we take a sequence of d-regular graphs with the girth diverging to infinity, and suppose the parameter lambda satisfies and is at most d minus 1 to the d minus 1 over d minus 2 times d. Huh? d minus 2 to the power d. To the power d. And as a side remark, asymptotically, as d goes to infinity, simple exercise, that means that lambda is at most e over d. Okay. No, I made a mistake here. It's slightly different. It's d to the d over d minus 1 to the power d plus 1. I apologize for this mistake. This mistake has to do with the difference between the degree and out degree in a tree, and but I need it right so that I get my numbers correct. Okay, so, and the fact that it's something like this, okay, it's an exercise. Okay, suppose that's the case. Then, if you take a partition function of this of the graph, the partition function, as I said, is typically large, exponentially large. So it makes sense to, if we want to say something, now we want to say something about the limit of the partition function. What does it asymptotically look like? So we're going to take the logarithm of the partition function, divide by n, and the claim is that it converges to a limit. N is the size of Vn, as yes, it's a number of nodes. So n is the size of the Vn, number of nodes. Thank you. That converges to a limit. And that limit you can write as logarithm s of 1 over some number p, that I'll tell you shortly, p over 2, 2 minus p to the power d minus 2 over 2, where p is the unique solution of this equation. I really have to fix my powers versus time. P to the power d minus 1. Yes, p to the power d over 2. And let me put it here. Okay, so what this theorem says is that we can actually say something about, yeah, you had a question? No. We can say something about the asymptotically, the asymptotic value of the partition function. We can say something about the exponent of this partition function in deregular graphs, large curves, at least for some values of lambda. But really, because we're interested in counting, which is lambda equal to 1, then in that case, we can just see for what values of d that identity is true. So when 1 is less than or equal to d to the d over d minus 1 over d plus 1, and then that turns out to be the case for d equal to 2, 3, and 4. Okay, I'm not going to do that here. You can verify it yourself. That means that in these cases we can actually, the limits of the partition functions, log-partition functions of this graph, or in other words, the number of independent sets, we know asymptotically. And let me just tell you what they are. And actually, let me sort of write it in somewhat less formal. Okay, that's fine. I'll leave it like this. This limiting value, which comes from solving this fixed point equation, you can compute numerically. And I'll tell you what it is. In case when d is equal to 3, and 2, 3, and 4, and 5. When d is equal to 3, that's the first interesting case. That's a log 1.545. This case is log 1.49. In this case, it's log 1.45. The numbers are not important. So this is d equals 3, 4, and 5. The numbers are not important. The important is that they are there and we can compute those. So it means that in these graphs, the number of independent sets, for example, in 3 regular graphs with large curves, the number of independent sets is asymptotically 1.545 to the power n. Yes? You can get some error bounds, and we will actually, okay, that's a good question to keep in mind when we do the proof. Now I want to go through the proof, and it's good error bounds, but off the top of my head, I don't remember qualitatively. Huh? Something with? Yes, something reasonable. It's not going to decay like 1 over log something. It's going to be, I think it's a power law. All right, so now I want to go through the proof of this theorem and illustrate the proof of this theorem as an illustration of the correlation decay method and local method. So that's what I want to do now. Unless there are any questions. Any questions about so far? No? Okay, good. Yes? Yes. No. It turns out, but that goes outside of the scope of this lecture, it turns out that lambda is larger than this critical value. It is no longer a property, it's no longer uniquely defined by the fact that it's a irregular graph with large girth. Further details of the graph are important in that case. So that's, and the way to see that, by the way, okay, good that you asked this question. The way to see that is that when lambda is very large, as we observed, it sort of corresponds to the largest independent set. Can the largest independent set of a graph be more or less the same as long as the graph is irregular and large girth? The answer is no, because if you, for example, you can take a bipartite graph, which is irregular. In that case, you have an independent set which is a half of the entire graph. At the same time, that takes some work, but if you take a random irregular graph, it will have a large girth, short of little correction that you have to worry about, but more or less. It has a large girth, but largest independent set is ratio is strictly less than half, something like 4.48 or something like this, strictly below. So this theorem cannot be possibly true for all lambda. But below that regime, somewhat surprisingly, it's just the fact that it's locally tree-like, irregular, it's good enough. So, yes, and that we will that's something that we will do now. So now what I want to do is, since we somehow think that this business has something to do with, since the irregular graphs with large girths locally look like trees, let's do first an analysis on a tree. So that's a step one. Trees. Let's count the number of independent sets on a tree. That's not a difficult algorithmic question, but we do it for a different reason, to get some handle. So here we have a tree, and here for convenience, I will make it so that, well, the degree of the root is d, but I will assume that the degrees of all the out degree of all the neighbors are also d. So for convenience, I'm gonna perturb my tree. It's no longer the case that all the nodes have degree d. The root has degree d, but the neighbors have degree d plus 1. But I do that so that the out degree of this node and all the further nodes, except for the leaves, and leaves obviously have degree 1, is preserved. And this, somewhat jumping ahead, this has to do with the fact that when we look at the node within a graph, this node has degree d, but neighbors, if we delete this part, the neighbors have degree 1 less. So, and we will deal with this fact later. But now let's start with this tree. Okay? So is everybody clear? We have degree d here, and all the out degrees here are also d. Yeah? And let's derive a couple of useful identities. Suppose the depth of this tree is t, little t. For convenience, I will denote the partition function associated with this entire tree, now z sub t, as opposed to z sub the graph as would be appropriate. This is a number of, and Also, to make things simple, let's just make lambda equal to 1. It just simplifies the derivation a bit. So therefore, we're just counting independent set on this tree. The total number of independent sets on this tree, what is it? Well, it comes in two simple flavors. First, there's two possibilities. Either the root belongs to the independent set or not. So I will write it, with your permission, write it like this, introduce the following notation. This is the number of independent sets with the condition that the root V0 does not belong to the independent set. And then you have the rest plus all the independent sets where the root belongs to the independent set, clearly. One of the two. Okay? Now observe the following things. This thing will remain the same. This, let's focus on this case. So here's your root. We're counting all independent sets containing this root. What happens with neighbors? If the root is in, the neighbors are out. Right? So all the neighbors are out. And then they have their own subtrees. So the number of independent sets in this tree which contain the root then is the same as the number of independent sets in the remaining part of the graph with these nodes out. Well, I claim that this is simply zt minus 1. I'll write it down, and then we will convince ourselves. Okay, so product over all the neighbors. So call this is V0, neighbor V1, neighbor V2, and so on. Vi not in the independent set. So what I'm saying is that that second object, you can think of it as the number, as a product of independent sets, of the number of independent sets in each subtree. But in each subtree, the node, the root, is excluded. So it has to do, now, exercise. That's important to make this observation. If you have two graphs which are disjoint, so you have graph G1 and G2, and which are disjoint, then what is the relationship between the number of independent sets in this disjoint union of two graphs versus partition functions of each individual graphs? It's a product of two. ZG1 times ZG2. It's a product. Again, it's one sort of basic graph theoretic facts that you have to convince yourself, but I'll leave it as an exercise. So here, because the node is already in, and then the remaining part of the graph is a disjoint union of D trees, when in each of them node has to be out, so therefore we have this identity. Okay, so far I'm just, looks like I'm manipulating, I'm going to manipulate this further and write it like this. This is equal to, so we're going to divide both parts of this identity by this term. You get 1 plus product from 1 to D, Z t minus 1, Vi not in the independent sets, divided by Zt. Now I want to also interpret this term ZT. ZT is the number of independent sets with simply the root being out. So that picture is no longer relevant. We have these neighbors. That object is the number of independent sets with the root out. Yeah? Now if the root itself is out, what's the implication for the remaining part of the graph? There is no implication, right? These nodes can be in or out. It doesn't matter. So then, this node is out, the edges are deleted, you have this joint union of trees, then what you simply have is a product of partition functions of all of these trees. They're all identical, so it's just one object, which is simply ZT minus 1. Any questions so far? Why do we do this kind of manipulation? We do that because now we can actually interpret these ratios as probabilities. Specifically, that object over here is probability that in the original tree, the node, the root, does not belong to a randomly chosen independent set. Inverse. Just checking if you're paying attention. Inverse. Right? As we said, this was our first observation lemma that we did. Okay? So we have that. This is equal 1 plus. Now, what about this object? Exact same thing, but for the smaller tree. Tree with depth t minus 1. And all of these objects, by the way, are the same because it's just a labeling of the nodes, but all these trees are identical. That's where the regularity is important, and the fact that it's locally tree-like is important. So we have that this is equal to, oh, I did use notation p sub t, so no longer need to write it p sub zt, p sub t is equal to 1 plus, and then what we have here is p of t minus 1, that a generic node now, because it's any of this any of these nodes, that the root of the tree with depth t minus 1 does not belong to the independent set. And now it's not minus 1, but it's to the power d. Oh, because I said lambda is equal to 1 for convenience. Yeah? But otherwise, if there was a lambda, you would just put it would be just this factor lambda here. It would come from the fact that you would have to have a factor lambda here because you've included this node. So it's a small modification. But we just do it for lambda equal to 1. Okay? So we have this identity. We have this identity. So what? Let's work with this identity. And now just take this identity as a sort of abstractly. So this identity looks like something like we have essentially recursion. P sub t minus 1 is equal to 1 plus p t minus 1 to the power d. Or put it more normal form, pt is equal to 1 over 1 plus p to the pt minus 1 to the power d. Okay? So that's a recursion. Perhaps that recursion, we can say something about the long-range behavior of this recursion. What does it converge to? Does it converge to? And things like that. Well, this is where this condition lambda less than d, in this case, degrees d to the, so degrees d to the d minus 1 to the d plus 1 comes into place. So I'm going to tell you some fact and leave the proof as an exercise. It's not too complicated exercise. It's not too complicated exercise, doable, but it takes a little bit of calculus work. Let's put it this way. If this property is true, if lambda is less than 1, lambda is less than that quantity, and for generic lambda we have to look at this identity. Alternatively, lambda is equal to 1 and d is 1, 2, 3, 4, and 5, so that this identity is true. Then for every starting point p0 in the interval 0 and 1, pt converges to limit, and this limit p bar satisfies is just, not surprisingly, a unique solution to this identity. So again, if there is a limit, it's better be the case that you just simply substitute the limit here and here, and the claim is that this indeed is the case. There is a limit regardless of the starting point. Where is this coming from? Where is this property? Why is that property true under this condition, not true in the other condition? I said I'm going to leave it as an exercise. I want to give you some kind of idea why is it true. If you look at the function f of x, 1 over 1 plus lambda x to the d, let's just plot this function. And that function, okay, when x is 0, it starts with 1. And when x is 1, it's 1 over 1 plus lambda. And it looks something like this. And this is just a diagonal. So this is a plot of function f. Unfortunately, that doesn't give enough insight as to long-range behavior of this iteration. So instead, let's look at the two iterations of function f. So take a double iterate of this function. Take f of f. So instead of x here, substitute f of x. The original function was monotonically decreasing. This function will be monotonically increasing. So I'll delete the f function here and plot second iterate of f. Shall I just yell and speak loud? Okay, I'll try, although this limits my... okay, so when you look at the second iterate of function f, then it's a monotonic function, and that's where you see the dependence on behavior, whether lambda is smaller than this quantity or not. Turns out if the lambda is smaller than this, the function looks sort of like this. It's monotonically increasing, intersects diagonal only once. However, if the lambda is bigger than this quantity, that function has 3 intersections with the diagonal. And the implication of this is that now it becomes a simple sort of calculus/topological exercise. If there is only one intersection with the diagonal, then when you iterate this function, regardless where you start, you're going to end up in this point. Right? So now this fact has nothing to do with graphs and trees and anything like that. It's just a simple calculus. But if your function behaves like this, then if you start here, you're going to get stuck here. If you start here, you're going to get stuck here. And from this is the unstable point of the recursion, you're going to be pushed away. All right? Unfortunately, for our case, we do need this convergence for every starting point. Why? So now, okay, so we've concluded something, right? So we've computed the limit of the probability that the root is out of the independent set in this deep tree. We've done that, but it's not clear whether this has anything to do with computing the partition function on locally tree-like graphs. We have to make a connection with that point. So I'll make this connection, and I'm already running a little bit out of time, right? So it's a 1 hour lecture. Go ahead. I will try not to abuse your patience. I will go ahead for another 5 minutes, and then I'll stop. So one thing is to compute this probability, the node is in or out on a tree. The other thing is to do that on a graph. Because even if it's locally tree-like, but you start expanding from the node to its neighborhood, and so on, and so perhaps do it like this, and so on. It used to be a tree now, but now, besides the tree, you have this entire rest of the graph present. So, and that rest of the graph has impact potentially on this probability. Now we're going to make the following modification on this exercise, on this derivation that we've done. I'm going to draw this tree again, a lot of trees in this lecture. And consider the same problem, the probability that the root is not in the independent set on this tree, but now I'm going to put a boundary condition. The boundary condition is on the set of leaves of this tree, and it's of the flavor that some nodes I declare to be in, and some nodes I declare to be out. And so on, right? So same thing as before, but look at the probability that the node does not belong to randomly chosen independent set. But now I condition that this independent set happens to be such that these nodes are in, and for example, okay, so this and these nodes are in, and these 3 nodes are out. And there's no pattern here. It's absolutely arbitrary but fixed pattern. So now that becomes a conditional probability, quantity. And you no longer can write it as in any nice form of this, like here, because now your trees have their own separate boundary condition, and this probability, this recursion is no longer true. However, the nice thing about this is that you can actually bound it from above and below by pt and pt minus 1, or pt minus 1 pt, same thing here, depending on the parity. And I don't remember the parity exactly, but that's besides the point. The point is that, in fact, that quantity, that probability that we did for pure case, without any boundary condition, provides simultaneously an upper bound and a lower bound for this probability with an arbitrary boundary condition. Let me tell you why this is the case. This is the case because there's two steps in showing that. First step is the monotonicity. Monotonicity in the sense that if I switch the status of one variable from being out, so it used to be out, and now I switch it to being in, that impact is monotonic. That makes less likely for the neighboring node to be in. So if I do it for all nodes, so now if I consider a boundary condition where everything is in, the distribution here drops down. And if I consider the boundary condition where everything is out, the distribution here pumps up. That's the step one. The step two is to observe that these two boundary conditions we have in fact already analyzed. Because this boundary condition where the nodes are out is simply pure tree case with one small level. So having these nodes out is the same thing as just ignoring this layer altogether and looking at the case t-1. That's an exercise to figure out that that's the case. And the second case where all the nodes are in, what do you think it corresponds to? t-2. It's just two layers out. So this is in, this is out. And therefore that's t-2. Good. And then, as you see, there's a parity here, and but that parity is besides the point. But what we know is that pt converges to the fixed point. pt converges to the fixed point, and therefore this probability with arbitrary boundary condition converges to the same fixed point. And therefore this boundary condition is actually irrelevant. Probability that the node does not belong to the independent set with boundary condition is asymptotically p bar. And that's the crucial observation in this development. Then to connect it to the computing the partition function limit, we use this representation that partition function is a product of probabilities inverses. This probability we sort of computed approximately. So it's almost like we're done here. There is a big caveat here. The caveat is that when you start deleting nodes from the graph, it stops being a regular graph. Therefore, just like that, it doesn't work. There is a modification to that which is specific to this particular theorem, and I can tell you offline how to do that. The idea is that to modify, after you delete some nodes, you modify it with some extra connections to preserve the regularity, and you have to study the impact of that extra step. But it's done using exact same analysis as before. And then by studying these marginal probabilities and the impact of additional edges, you can derive this theorem. So I'm sorry for taking it. No, you can do that. So okay, so that's question times. So the way this can be done is as follows. So you have a node, some neighbors, and then you have the rest of the graph. What you do is you take another node which is far from it, at the diameter sort of distance. You delete this node, we know that how to recurse on inverse probabilities here and here, but we know that when we delete those nodes, we lose regularity. So what we do is now we connect these neighbors. That does not destroy Gauss condition because we were carefully in choosing the sparse amounts. 2 nodes at a time. So the one basic step corresponds to deleting 2 nodes at a time and connecting all the neighbors by edges. And that you need to see the impact of this one type of transformation, and log partition function limit is just a power of that quantity. This method, actually, this idea of looking at this marginal probability and computing them approximately, it's called the cavity method in physics. If you see cavity method, that's sort of one flavor of it. Other questions? I don't know if we have time for questions, but yes? We are using that to handle the boundary condition, because you see, good. So you see, these recursions have a starting values, right? So we did. I assume you buy that you can actually bound this boundary condition by pt minus 1 and pt minus 2, right? Now, the starting point of these recursions might matter unless you have a convergence to the same value. So if you do not converge, then starting here you converge, like in this example, starting here you converge to this point, starting here converge to this point. Your probability boundary condition is somewhere, conditional probability is somewhere in between, and therefore you don't have any conclusion. But if you converge from all starting configuration, then you converge to the same limit, and that conditional probability is kind of sandwiched from between these recursions with arbitrary starting configuration. Yes, that's the thing. The odd and even starting points are different, and we want them to converge to the same point. And if you have that picture, the odd and even starting configuration will not converge to the same value, and things are inconclusive, and no conclusions can be drawn. On trees without boundary condition, yes. On trees, what? Yes. So if you are above, so the question is, suppose you are above the boundary condition. Suppose you are here, and therefore the picture is like this. So, and you look at on trees without any boundary condition, yeah, what's going to happen is that if the depth of the tree is even, you will converge to this point, and the depth of the tree is odd, you will converge to this point. Or maybe the other way around. It doesn't matter. But the point is that even and odd limits will be different. One will be this one, one will be this one. Yes, that much you can conclude. But unfortunately, it doesn't tell you anything about this probability with arbitrary boundary condition. And that's something you need to place this gadget in the bigger graph. Because the impact of the rest of the graph on this, on this separator is completely non-trivial. We've trivialized it by saying that it actually converges to the same quantity. But in general, the rest of the graph acts on this boundary in some non-trivial way that depends actually on the details of the graph. And therefore, we cannot make any conclusions. Thank you.